Hi, this is Cecil Bozarth again. So far in this course, we've talked about the domain of operations and supply chain management activity, and we've also talked about process choices within manufacturing and services, including the trade-offs associated with different process choices, the role of customization, etc. Now we're going to start turning our attention to capacity decisions. Think about it this way. Organizations have to match up demand with their internal supply or the supply of their supply chain. And those decisions happen at the very strategic level all the way down to individual process level. So we're going to look at this from several different levels, but we're going to start with an analysis of strategic capacity decisions. This lecture is divided into four main parts. First, we're going to quickly define what capacity is. We're then going to differentiate between strategic and tactical capacity decisions. Keep in mind that within any organization, strategic and tactical capacity decisions are being made simultaneously. We'll then talk about different strategies for how to add capacity in terms of when do we add the capacity and how much. Finally, we'll talk about evaluating capacity alternatives, and this will make up the bulk of the lecture. We'll review economies of scale and difference points and break-even points, topics you've very likely had in other classes or in your previous career. We'll then spend our time talking about expected value analysis with a decision tree. What expected value analysis does is it allows us to summarize situations where we have multiple possible demand scenarios and multiple capacity alternatives, and it allows us to summarize that in a meaningful way. Expected value analysis is going to come back when we talk about this Genentech case. The Genentech case is going to be a lot more complex than what we're going to do in this lecture, but hopefully we'll give you a start into it. Finally, we'll talk about learning curves. The idea behind learning curves is that the same resources, whether they're people, processes, machines, whatever, typically become more productive over time due to learning. So when this happens, you have greater effective capacity with the same resources. And we have to take that into account when we're evaluating capacity alternatives. So what do we mean by capacity? Simply put, capacity is the ability or the capability of a worker, machine, work center, plant, organization, some resource unit to produce output per unit of time. So there's a couple key points there. It's an idea of we're producing output and over some period of time. To give you several examples of how we might measure capacity in different organizations, an assembly line might measure capacity in terms of units per hour or a day. A quick oil change place might look at oil changes per hour they can provide. A consulting firm or software developers might look at capacity in terms of billable hours per week. And finally, a college might look at student hours per semester as a measure of capacity. Now, if you look at these different measures of capacity, one of them is relatively different from the others, and that's billable hours per week. All the other measures of capacity here look at capacity in terms of outputs. Billable hours per week, however, is looking at capacity in terms of the inputs. Why the difference? Well, generally speaking, if you're in an operations environment, whether manufacturing or services, that makes a standardized product or service, you tend to measure capacity in terms of outputs because the output units are comparable. On the other hand, the more customized you get, the more less generic, I would say, in terms of the outputs of your products or the outputs of your service environment, the more likely you are to measure capacity in terms of internal inputs. Another point I want to bring up here is the key difference between services and manufacturing when we talk about capacity. And that is that manufacturing can often store capacity in the form of inventory. They can store that capacity in terms of finished products, components, subassemblies, whatever. Services often don't have that opportunity. It's not exactly like a hospital can say, okay, we're going to do a run of broken legs here that we're going to set, and then we'll pull those out of inventory when people come into the emergency room with a broken leg. Because of that difference, in some ways, it's easier to manage capacity in a manufacturing environment. We can either provide capacity live to handle a customer's requirements, or we can pull from inventory. Services often doesn't have that flexibility. I alluded to earlier the idea that we have to differentiate between strategic and tactical capacity decisions. So how do we do that? Well, think about strategic capacity decisions that typically take 1 or more years to implement, and that's what I mean by 1 or more years out. Traditionally, these were known as bricks and mortar decisions, but they don't necessarily have to involve the building of an actual facility. It could involve, for instance, the implementation of a future technology. Maybe we want to move all our computing to the cloud, and that's going to open up our abilities. Well, you're not going to convert over to cloud computing overnight. Examples of strategic capacity decisions are putting in a new building, maybe offering a new degree program like the online MBA. In the case of Genentech, the case study we'll talk about, Genentech has to put plans in place that can take 5 years and $600 million. These are strategic decisions. Another aspect about strategic decisions are they are expensive and very difficult to reverse. Tactical decisions, on the other hand, are typically things we can do in a time frame out to a year or so. We have a little bit more flexibility to do it. For instance, we can adjust workforce levels. We can offer additional shifts. We can maybe build up or pull down inventory levels. We can subcontract. Examples of tactical capacity decisions would be class sections offered. For instance, think about the online MBA. There was a strategic decision to offer the new degree program and put in place the resources to do it. A tactical decision might be how many different courses are we going to offer? What kind of electives might we offer in the future? In the case of a manufacturing firm, the strategic decision would be to put in place a new plant. Production campaigns, on the other hand, might involve what mix of products we're going to make within that plant. So following on that idea of strategic versus tactical capacity decisions, the further we go out in time, the more likely we are to be dealing with strategic capacity decisions. These are those bricks and mortar decisions. They involve high-level planning. The data is relatively aggregated in terms of what the demands will be, what the marketplace is going to look like. They tend to be high-risk decisions as a result. Imagine if you are a Genentech and you're trying to figure out what the demand for a particular drug is going to look like 10 years from now. Well, what can happen over that time frame, not only in terms of the regulatory environment, but in terms of competitors' actions? There's a lot of risk there. Tactical capacity decisions, on the other hand, are typically done within a shorter time frame, but a key point to remember is that tactical capacity planning has to be done within the limits defined by strategic capacity decisions. So in other words, once you've decided to build a plant of a certain size, if you're Genentech, that limits what you can do tactically. Likewise, there's a third level we really haven't talked about, and it's really not necessarily capacity planning per se, as much as simply trying to make the best use of the resources we've lined up. And we call that planning and control. So just as tactical capacity planning is constrained by strategic capacity decisions, planning and control decisions are constrained by the tactical plans. This is where we get into the day-by-day or week-by-week decisions about what we're going to do, given the workforce level we have, given the inventory levels we have. As we go from strategic to planning and control decisions, the risk lowers. If you get to the planning and control level, the focus is really on adjustment and execution. We're not trying to make long-term decisions or guesses about where the marketplace would be. Now, if you notice, I have some blue shading there. The blue shading in the back of the slide implies a possible range of outputs we have. Obviously, the further we go out, the greater range we can have in capacity. We can either add capacity or shrink capacity, whatever. As we get into days or weeks out, we have really limited ranges of capacity. We can neither add a lot of capacity or get rid of a lot of capacity very quickly. So while I've distinguished between tactical and strategic capacity planning here, keep in mind that there's day-to-day things going on which we call planning and control. But all these activities are going on simultaneously within an organization. As your career develops, you'll probably move from planning and control to tactical planning to strategic capacity planning decisions. So one of the questions that often comes up is, when should we add capacity and how much capacity should we add? Let's suppose for a moment that we have determined or we have forecasted the demand level for a product or service over some period of time. And by the way, we will get into forecasting techniques later in the course. And so we have a line that looks something like this. The question is, how should we go about trying to meet that demand? One alternative is to follow what we call a leader strategy in terms of adding capacity. And there's actually a couple advantages to doing this. And can you think about what those are? Probably the biggest advantage of following a leader strategy is that we reduce the likelihood of running out. Remember that a demand forecast is just that. It's a forecast. We could be wrong. So if we have excess capacity, it reduces the likelihood of we're going to run out, but of course we're going to do that at a cost. When might we do this? Well, imagine if we're in an industry where we have a product with a potentially very high margin. That means that the revenue we can get for it is much, much higher than the cost. In a case like that, we certainly don't want to turn away demand. We might be willing to take on the risk of having excess capacity and paying for it versus having to turn away business. Another advantage of a leader strategy is that we're not trying to run near our theoretical capacity. And as we'll talk about later on in this course, as we start running a facility or running a group of people or a business process near its quote-unquote theoretical capacity, funny things happen in terms of length of time in the system, queue sizes, etc. By keeping our utilization levels relatively lower by having some excess capacity, it often makes it easier to manage the facility. But of course, that's going to be at a cost. Finally, building in chunks is often cheaper than trying to match demand over time by adding little increments of capacity. One of the things that comes up in the Genentech case is the idea that building a facility twice as large as another facility increases the cost by the square root of 2. And probably what goes into that rule of thumb is the idea that you build a building twice as large, it's not going to be twice the cost, but also there's all the overhead associated with planning, etc. So that's a leader strategy. Alternatively, we could follow a laggard strategy. The benefits here are really exactly the opposite of what it is for a leader strategy. In this case, we're in a business situation maybe where there's really not any great advantage to being able to meet all the demand. We want to kind of err on the side of being sure that we can keep the facility fully utilized. An example here might be a license bureau where we're giving out licenses to people. We don't want to have a lot of workers sitting around waiting for potential drivers or people who need their tests to come in. We'd like to keep those folks fully utilized, so we're only going to add capacity when it's absolutely necessary. Now in this particular case, we are talking about maybe keeping the facility utilized near its theoretical capacity, so we get the greatest productivity out of the resources in this particular example. And then finally, we can try to match the demand as best we can. Now, when I show this line here for matching and also for the other two strategies, keep in mind we don't necessarily have to do that all internally. Our capacity strategy could involve using key suppliers or subcontractors to do that. When would I do something like a match strategy? Again, where the relative balance between stocking out, or I shouldn't say stocking out as much as running out versus having too much capacity, when those costs are relatively balanced, maybe a match strategy makes sense. Now let's put this in the context of the Genentech case, which we're going to talk about. When you read through the Genentech case, look at what the potential revenue is associated with the drug they're making, and think about what the margins are like. And then think about, do you want to risk having too little capacity and not being able to pick up those margins because you didn't have the facility, or would you be more willing to have an empty $600 million plant? That's kind of the choices that they're facing in that case. Southwest Airlines, think about this in the context of Southwest Airlines. What is the advantage of Southwest Airlines to have gates that aren't fully utilized? Well, one of the potential advantages of having extra gates is it gives you some flexibility to respond when there's schedule changes or delays or whatever, but obviously at a cost. So it's not a trivial decision to make, obviously. Okay, With that background, let's get into evaluating capacity alternatives and some of the different tools we can use. The idea of economies of scale has been around for quite a long time. The idea behind it is that when we look at a productive facility or unit, plant, whatever, we can look at costs in terms of fixed cost and variable cost per unit. The fixed cost is what we have to pay for things like building, basic salaries, insurance, whatever, and that's not going to be affected by the level of production. The variable cost, on the other hand, does go up or down based on the level of production. Classic examples of variable cost are materials used. So let's suppose we have the total cost for a fictional line process, and it's expressed as a fixed cost of $200,000 plus $4 in variable costs for each unit we make. And again, in this particular case, maybe that variable cost includes materials and labor, maybe includes some other things. So the question becomes is, if we make just one unit, what's the cost of that unit? Well, the cost of that one unit would be the $200,000 fixed cost plus $40 of variable cost, or $200,040. Conversely, what if we make 10,000 units? Well, what happens in that case, we have $40 of variable cost per unit, or $40,000 of variable cost, but the $200,000 fixed cost doesn't change. So the total cost for the 10,000 units becomes $240,000, or about $24 per unit. The big aha behind economies of scale is as you increase production levels, the cost per unit drops. Now, that said, probably up to about 30 years ago, the whole mindset in the manufacturing world was greater economies of scale because we can drive the per unit cost down. The problem, as we probably can imagine from the Porter article and what is strategy, is that if everyone tries to drive their costs down through higher production levels, then we really don't have any differentiation in the marketplace. There's certain types of industries where maybe per unit cost being the lowest isn't where we want to compete. So economies of scale, while it's a good tool to understand how costs behave as production levels rise, it's not the only thing we need to consider when we're evaluating capacity. In difference points, take the cost models we've talked about in economies of scale, the idea of fixed cost versus variable cost, and uses that to compare how costs behave across multiple capacity options. What an indifference point is, it's basically a point at where the costs for two different options are equal to one another. So let me set up the case here. Suppose I'm Ellison Seafood Company, and I have to make a decision about whether I'm going to use a common carrier, a contract carrier, or my own privately leased truck to make deliveries. So I'm making deliveries of seafood here. If I use a common carrier, someone I can call up in the phone book, there's basically no fixed cost, but every time I make a shipment, it's going to cost me $750. On the other hand, I could get a contract carrier. Maybe what this means is once a year, I pay them $5,000, which gives me the right to make shipments at a cost of $300 each. So I pay a little bit of money up front, but it brings my variable cost per shipment down. Finally, I can maybe actually lease a truck of my own. It's going to cost me $21,000 a year. That'll be insurance, payments, etc., basic maintenance. And there'll be a variable cost per shipment. So maybe what that variable cost involves is the actual gas and driver time. So if we look at these three different capacity options and there are three different cost functions, and we try to graph it up here, we get something that looks like this. Let's take the red line for a second. That's the private option here. So even if we make no shipments at all, it's going to cost us $21,000. But the costs are going to go up by $50 per shipment we make. So we get a relatively flat line here. On the other hand, look at the black line here, which is for the common carrier. If we make no shipments, costs are zero. On the other hand, as soon as we make one shipment, it's $750. Two shipments, $1,500, etc. So you see the slope of this cost curve is relatively steep. So now I start looking at these, and what do I notice? Which capacity option is best? Well, first of all, what do we mean by best? If we mean by cheapest, then it's going to depend on how many shipments we expect to make. If we're only going to make 3 shipments, then obviously the common carrier would look best. On the other hand, if we're going to make more than 70 or so, then maybe we need to be leasing or a truck. Maybe we need to go with the private option. Anywhere between here, roughly about 12, what looks to be about 67, a contract carrier seems to be best. And in fact, I can get even more precise by saying, where is the point at which these cost curves cross? So let's look at this at one point right here in more detail. I might be interested in at what demand level we're indifferent to using a contract carrier versus buying or leasing our own private truck. And this is what we mean by the indifference point. So what I do is I set the cost curves for the contract carrier equal to the cost curve for the private truck, whether we're leasing or buying it, and basically solve for X, which is a number of shipments. So in this particular case, we've got to be sure we understand demand level is number of shipments we seek to make. And it turns out, if we do the basic algebra here, once we get to about 64 shipments, we're indifferent to either one of these. So if we go below 64, go with a contract carrier. If we're going to go above 64, go with a private truck. If we're not sure exactly how many shipments we're going to make, then we have a decision to make. We need to understand something about the possible range of outcomes, and that will lead to our expected value analysis type of approach. Another tool is break-even point. In break-even point, now we actually bring revenue into the analysis. So far, we've just looked at cost in terms of economies of scale and indifference points. Break-even actually asks the question, at what point does revenues equal cost? So in other words, how high does production have to be, or how high does the demand have to be for us just to cover our cost? Another way to think about this is, once we get past the break-even point, we actually start making money because we've covered our fixed and variable cost. Suppose, for instance, we've got a operation environment where we have a fixed cost of $200,000. We got a variable cost of $4 per unit. It's at a fictional assembly line we're talking about earlier, but now we know we can sell each unit for $100. So at what point does the revenue we generate cover the cost? Doing some basic algebra, it turns out to be 2,083.33. The way we interpret that is, then we have to sell at least 2,083 units just to cover our cost. After that, we start making money. Now, why do we want to look at this? Well, once again, if we're looking at various capacity alternatives, we have to have some idea what the demand levels are to evaluate them. If we don't think our demand's ever going to get above 2,000, this is not going to be an attractive capacity option. We may need to look at something else with a relatively lower fixed cost and maybe a relatively higher variable cost. So with that background, let's turn our attention to expected value analysis. What expected value analysis does is it summarizes the expected costs, revenues, or profits, or some other financial outcome of multiple capacity demand scenarios. So we use expected value analysis where we have a relatively high level of complexity in terms of our options and possible outcomes. The best way to describe expected value analysis is through an example. Let's suppose we're looking at Pennington Cabinet Company. And Pennington Cabinet Company has three possible capacity options that they'd like to consider. They can stick with the current facility, which has a fixed cost of $1.2 million and a variable cost per unit of production of $300. Furthermore, this current facility has a maximum yearly output of 3,000 units. Alternatively, they can add a new line within their existing building. That'll bring their fixed costs up to $3 million. It'll help drop the variable costs per unit down to $200 through greater automation, and it'll increase their maximum yearly output to 5,000 units. Alternatively, they may actually have to build a new plant altogether, in which case the fixed cost will now rise to $4.2 million, but again, the variable cost will drop to $150. Now, as we're looking at this, obviously, if you've got a capacity option with both higher fixed costs and higher variable costs than anything else, it's probably never going to be a very good option. So to have some trade-offs that are interesting here, we start seeing these differences these trade-offs between fixed and variable costs. And this is typical of what you'll see in industry. If we go with a new plant, by the way, it brings our maximum yearly output up to 7,000 units. Another way to express those maximum yearly outputs are as effective capacity. We may not use all that capacity, but it's there if we need it. So those are the capacity options. What I've done here is shown those capacity options in decision tree format. So I start off here with a big square, which implies I've got a decision to make about what capacity option I want to go with. And by the way, we have to decide on one of these three. I guess an alternative could be go out of business, but that would be a fourth branch. It's not one we're looking at here. So if I look at the current capacity option, what is the financial output going to be? Well, it's going to be the demand met times the price minus the variable cost. That's the contribution per unit of demand met minus those fixed costs. So take a second to think about that formula and see if that makes sense to you. You plug in whatever you think the demand is you're going to meet. You multiply that by the difference between the price per unit and the variable cost per unit, and that gives you the contribution per unit, and then you subtract out the fixed cost, and that'll give you the profitability of going with the current capacity. Alternatively, if we go with a new line, the formula looks pretty similar, except of course we have different variable cost and different fixed cost. And finally, if we go with a new plant, demand met times price minus the variable cost of 150 and the fixed cost of 4.2 million. So all I've done is taken my three capacity options and showed them in a graphical manner. Now that we've talked about the capacity alternatives, let's talk a little bit about the possible demand levels. Now, a point of clarification here. In the real world, you wouldn't expect demand to fall into just three possible points, like, oh, the demand's either going to be 5,000 units, 2,000, or 7,000. You might expect the possible demands to follow something more like a normal curve. And I understand that, and certainly that's true in the real world, but for purposes of analysis, it's often easier to describe demand possibilities using a range of values with probabilities associated with it. So if I thought there's going to be a great deal of potential spread in demands, maybe I have numbers from 1,000 to 9,000 with different probabilities on it. But what I'm trying to express here, in effect, is what do I think the possible spread of demand is? And usually 3-point estimates is pretty good. One of the things to remember too is it's often very difficult in an environment where you're making strategic capacity decisions to be as precise as we might want. So if I can get three estimates of what I think the demand would be with likelihoods attached to them, that's going to be relatively qualitative and involve some management judgment. But it's a good thought exercise to think about how we would do that. So that's just a little bit of a qualification here about where these types of estimates come from. In a lot of cases, it's going to be based on managerial judgment. So I have three possible demand scenarios here with different likelihoods. And notice I have the percentages add up to 100%. How I would express that in decision tree format is now instead of a square, I've got a circle in three branches. The circle tells me that this is not something I can choose. In other words, when I was talking about capacity options, I can select whichever capacity option I want. I can't select the demand level out there. I mean, I may be able to affect it through advertising or something else, but for the most part, it's an exogenous variable. It's determined outside my control, and that's what I'm trying to emphasize here. We get to this branch here, and there's a 20% probability we go one way, a 50% probability we go another way, and a 30% probability we go a third way. So what have I done here? What I've done here is try to express this problem in terms of the capacity decision I have to make and then the possible alternatives that can occur based on that. So looking through this decision tree, if I decide to go with current capacity, I have a maximum effective capacity of 3,000. If demand turns out to be 2,000, then we're going to have some financial outcome. If demand turns out to be 5,000, I'll only be able to meet 3,000 of those. Notice, even though the potential demand is 5,000, we can only meet 3,000 of it. So it's sort of like saying we get up to our maximum. Finally, we could have what we call high potential demand, but again, we'd only be able to meet 3,000 of it. So what I'm trying to express here is if we go with current capacity, there's three possible outcomes. We can meet a demand of 2,000, or we can meet a demand of 3,000, or another demand of 3,000. Alternatively, if we go with a new plant, we have a 20% chance of getting a demand of 2,000, we have a 50% chance of getting a demand of 5,000, and we can pick up all that demand, or we have a 30% chance of picking up a demand of 7,000. And again, in this particular case, our maximum capacity for the new plant is 7,000, and our highest potential demand is 7,000. So we can pick up all the demand if we go with a new plant and if we go down one of those branches. So what I've got here then is a decision tree that summarizes the 9 possible outcomes. 3 capacity alternatives multiplied by 3 different possible demand alternatives. So I encourage you to take a second and make sure you're comfortable with the way I've described this decision tree and make sure I haven't left anything out of it. Now that you've had a chance to review the entire decision tree, let's go back and actually calculate the financial result of each of the branches we talked about. So to do this, let's assume that the price per unit that Pennington Cabinet Company sells is $2,000. So therefore, the value of each branch is calculated as a demand met times the difference between the price per unit and the variable cost per unit minus the fixed cost. So the value of the current capacity / low demand branch is going to be 2,000 times the difference between $2,000 and $300 minus 1.2 million, and that comes out to be 2.2 million. And I've shown that right here. The value of that branch is 2.2 million if this is what occurs. Now, what if we stick with the current capacity, but the demand turns out to be medium, which, as you recall, the potential demand was 5,000, what we would call medium demand, and there's a 50% chance of that. However, since the current capacity is only capable of meeting 3,000 units, then we can only sell 3,000 units. So the value of this branch becomes 3,000 times the price per unit minus the variable cost per unit minus the 1.2 million, or 3.9 million. So what do you think the value of the last branch here is going to be, sticking with the current capacity and high demand? Well, without even doing some calculations, we can kind of look at this and tell. If demand turns out to be quote-unquote high, potential demand is 7,000, we could still only meet 3,000 of that. So the financial output, the financial outcome, I should say, if we go with current capacity and demand turns out to be high, is going to be the same as what it was if demand was medium, 3.9 million. So now we have the value for all the different possible outcomes if we stick with current capacity. What expected value analysis says is we can now take these outcomes, multiply them by the probability of each of these branches to get a weighted result. So therefore, the expected value for the current capacity level becomes 20% times 2.2 million and 80% times 3.9 million, or 3.17 million. So let's actually start to look at the financial outcomes. So let's look at the financial outcomes for each of the potential branches here. Let's assume for a second that the price is $2,000 per unit. That's what Pennington Cabinet gets from the customer. The value of each branch then is calculated as the demand met times the price per unit minus variable cost minus the fixed cost. So the value of the current capacity low demand branch is 2,000 times the difference between 2,000 minus $300. Remember, $300 is the variable cost if you go with the current capacity, minus a 1.2 million fixed cost, or 2.2 million. So this branch has a value of 2.2 million. Now what about the medium branch? Well, for the current capacity medium branch, we have a demand of 3,000 that we can meet. Even though the potential demand is 5,000, we can only meet 3,000 of it. So we take 3,000 again times the price per unit minus the variable cost per unit minus a 1.2 million gives us 3.9 million. Now what's going to happen for the third branch here where we have quote unquote high demand, a potential demand of 7,000? Well, again, since we can only meet 3,000 of it, the demand we meet is going to be 3,000, and as you can surmise from this, the financial payoff for that branch is going to be the same as well, 3.9 million. So where does the expected value come into play? Well, we have three possible outcomes for the current capacity option with different percentages associated with them. We simply take a weighted average of those different branches and we get the expected value for the current capacity level. 20% times 2.2 million plus 80% times 3.9 million or 3.56 million. That's the expected value of going with the current capacity option. Now what about the new line? Again, the new line has a higher maximum capacity of 5,000, so that means it can meet all the demand if demand is low, all the demand if potential demand is medium, but it can only meet 5,000 of the unit demand if the demand is high. Remember again, on this branch, the potential demand was 7,000, but we can only pick up 5,000 of it. So again, going through the same types of calculations, for the new line, low demand branch, it turns out we have a payoff of 0.6 million or 600,000. Why is it significantly lower than it was for the same type of branch for the current capacity option? Well, the difference is because of the higher fixed cost. But look what happens. If demand gets up to 5,000, if we can meet 5,000 units of demand, then we get a payoff of 6 million. Once again, we take a weighted average of these possible branches here, 20% times 0.6 plus 80% times 6, and we get an expected value for the new line of 4.92 million. So let's stop there for a second. If these were the only capacity options we have, and there's nothing that says we can do 2, 3, 6, or whatever, however many capacity options we want to look at, just looking at it right here, the new line has a higher expected value. And that may be the thing that sways our decision process. On the other hand, if you look at the current capacity option, it seems to be a little bit less risky because the revenue, I should say the financial outcome is anywhere from 2.2 million to 3.9 million. In the case of the new line, it's anywhere from 0.6 million to 6 million. So not only do we have to look at the expected value itself, but the range of possible outcomes to evaluate what the risk is here. So what do you think is going to happen when we look at the new plant? Again, the new plant has higher fixed cost but lower variable cost. If you guess that the range of possible outcomes is going to be even wider, then you're correct. It turns out, and you can run through these calculations yourself, that if we go with a new plant and demand turns out to be just 2,000 units, then we're going to take a bath of $500,000. If demand turns out to be 5,000 units, we can pick up all that potential demand and we'll get a payoff of 5.05 million. If we hit the jackpot, as it were, or we're very lucky and we put a new plan in place and the demand turns out to be 7,000 units and we pick it all up, then we get an 8.75 million payoff. The weighted average of these turns out to be 5.05 million. So now we really have a tough decision to make. New line, new plant have pretty similar, pretty close expected values, but the new line decision is significantly less risky in the sense that we don't expect to end up with a potential loss even under low demand for the new line, but that could happen for the new plant. Do you go with this the new line option or the new plant? That's a business decision that has to be made. All we're trying to do here with the decision tree and the expected value analysis is to lay out the options. So the conclusions for Pennington. Which alternative would you choose if you wanted to minimize the worst possible outcome or maximize the best possible outcome? Well, let's go back here. Obviously, the best possible outcome is the $8.75 million, which can occur if we get the new plant and the demand turns out to be high. But there'd be only a 30% chance of that happening. What do we mean then by maximizing the worst possible outcome? Well, what's the worst thing that could happen if you're Pennington? What's the worst thing that you don't have control over? Well, the worst thing that can happen is demand turns out to be low. So if demand turns out to be low, if you go with the current plant, you have a payoff of $2.2 million. If you go with the new line, you get a payoff of $0.6 million. And if you go with the new plant, the payoff would be negative $0.5 million. So in that particular case, if you want to maximize the worst possible outcome, you'd stick with the current facility. Once again, the decision tree and the expected value analysis doesn't make the decision for us. It simply structures the data in a meaningful way. The second question, why is it important to know effective capacity versus just raw or potential demand? Well, obviously in this case, if we didn't understand what the capacity limits were for the options, then we wouldn't be able to correctly figure out how much of the demand we could meet. How could this help future capacity decisions? Well, imagine this. What if we were doing this analysis and we noticed, like we do in the case of the current capacity, that we pretty much will not be able to meet potential demand 70% of the time, or I should say 80% of the time for the current capacity option. That's kind of telling us we're running up against a wall there. We may be leaving money on the table. Now, I will tell you, in future lectures, we'll get into how we actually precisely measure the effective capacity of business processes, both manufacturing and service operations. So for this particular lecture, take it as a given that we can figure out what those effective capacities are, but we will actually deal in more depth with that later. The final topic I want to introduce here is learning curves. Learning curves have been around since World War II, and they recognize that people and often equipment or other systems become more productive over time due to learning. The result is an increase in effective capacity. Example from my youth is, believe it or not, I used to actually work in an ice cream parlor, which was probably the worst human resource decision ever made. But when I first started out there, it would take me like 2 minutes to make a banana split, and I worked there for several years. By the time I left that place, I could make a banana split in less than 30 seconds from start. So my capacity for producing banana splits increased dramatically over time due to learning. I learned the shortcuts. I learned how to do things quickly. And at a more useful level, companies must plan for such increases in effective capacity, or they risk overestimating their capacity needs. In other words, if they don't consider the impacts of learning and over time how that's going to increase the effective capacity of their resources, then they may put in too much capacity to begin with. And that could obviously have some significant financial ramifications. So let's get to a formal definition of the learning curve, and then we'll relax a little bit. The formal definition is for every doubling of cumulative output, there will be a set percentage improvement in time per unit or some other measure of input. So let's assume for a second I am following a precise 80% learning curve. The idea behind this and where the name comes from is if we're following an 80% learning curve, let's say, every time we double cumulative output, then the amount of resources will be 80% of what they were before. So as an example, let's suppose the first unit we make takes 10 hours of resource. The second unit takes 8 hours. So we've doubled from a cumulative output of 1 to a cumulative output of 2, and the second unit takes 80% of the first. Now what do we have to do to double output again? Well, we have to go from a cumulative output of 2 to 4. And if we're following an 80% learning curve, then what's 80% of 8? 6.4. That's what you see right here. We double cumulative output again from 4 to 8, and 80% 6.4 is 5.12 hours. We double output again from 8 to 16, and you get the pattern here. So what we see here is some fairly steep learning early on, followed by a leveling out over time. Now, if you look at this, and what if I said we'd followed a 70% learning curve? Would that mean we're slower at learning or faster at learning? Well, actually, the lower the percentage, the faster the learning. So if we had a 70% learning curve, the first unit would take 10 hours, the second unit would take 7 hours, the fourth unit would take 4.9, etc. So if you really want to insult someone, tell them they're following a 110% learning curve. It would imply they're getting worse over time. Continue with the formal definition. The way we describe points on this curve that we showed before, we can estimate the time for the nth unit, t sub n, by taking the time for the first unit and multiplying it by n raised to the power of b, where n is the nth, the number of the nth unit, and b is a natural log of the learning percent divided by the natural log of 2. So if you look at the formula for b there, the way to intuitively think about that is if we have an 80% learning curve, for every doubling of output, it'd be the natural log of 0.8 divided by the natural log of 2. If we wanted to maybe describe a different kind of a learning effect where we saw an 80% learning for every tripling of output, we'd have the natural log of 0.8 divided by the natural log of 3. But let's stick with the classic definition of a learning curve here. Okay. Another example, software help desk. The first call a person does while they're training takes them 8 minutes to solve. The second call takes them 6 minutes. So just based on those two simple data points, what do you think their learning rate is? And how long would you expect the fourth call to take, or the 16th? Well, to get the learning rate, what I would do is I'd take the time for the second unit and divide it by the time for the first unit, and I get that ratio, I get 75%. So I would say this is a 75% learning curve. So what's the time for the fourth unit going to be, the fourth call they do? Well, I take the time for the second, and I multiply it by 75%, and that turns out to be 4.5 minutes for the fourth call. What about the eighth call, which would mean another doubling of output? Well, I would then take the time for the fourth call, multiply it by 75%, and I get the time for the eighth call to be 3.75 minutes. And this is the time for the fourth call, and this is the time for the eighth call. What about the 16th call? Well, if you can imagine, we're going to take 3.75, multiply it by 0.75, and you'll actually get 2.8125 minutes. Now, let's be reasonable here for a second. First of all, it's very unlikely we're going to follow this type of improvement precisely. Secondly, once we start getting into 3 or 4 decimal places, you know, that's a little bit shaky, but we're being theoretical right here. We're just approximating what we think the rate of improvement will be. So give yourself a second to make sure that you can calculate the results the way I did here. But this is just a very simplistic example. What I've done is I've taken the formula I gave you a couple slides ago and I put it into a handy table that shows the times or resources required for the X unit and the first X units. And I'm going to give you an example of how we can use this table. So let's first of all go take a look at it. Okay. First of all, let me explain what I've done here. I took that basic formula that determined the time required for the nth unit, and I went ahead and calculated it based on whether we had a 70% learning curve, a 75% learning curve, 80% learning curve, all the way through 90% here. So let's interpret this number right here. If we're talking about unit 1 and we're following an 80% learning curve, then the time for the first unit is going to be 100% of the time for the first unit. Not a surprise. What do I have down here? Well, the way to interpret that is the second unit will take 80% of the time of the first unit. The fourth unit will take 64% of the time of the first unit. The eighth unit will take 51.2% of the time of the first unit, and so on. So what you see here is as we go further down here, the unit numbers get higher, the amount of time it takes as a percentage of the first decreases. You're seeing the learning curve effect here. So what's going on in this column? Well, let's look right here, 1.8. The way to interpret this is the cumulative resources or time required for the first 2 units. So in other words, the first 2 units will take 180% of the resources of the first. Make sure you understand where that number comes from. Another way to look at this is I simply take the sum of all the numbers in this column up to that point. So I take the sum of 1, 0.8, 0.702, it gives me 2.502. I can interpret that as saying if we have an 80% learning curve, the cumulative time for the first 3 units will be 2.502 times the time of the first, or 250.2% of the first. Now what do you notice? Let's just take here the 10th unit. If we follow a 70% learning curve, then the 10th unit will take 30.6% of the time of the first. If we have an 80% learning curve, the 10th unit will take 47.7% of the time of the first. And if we have a 90% learning curve, which implies the slowest learning effect here, the 10th unit will take 70.5%. Make sure that intuition works for you. Okay, so let's go back to the PowerPoint for a second. Let's suppose we have a situation where the first unit costs us $25 to make, and we think there's going to be an 85% learning effect on the cost. Now let me put a big asterisk there. Traditionally, learning curves were used to describe improvements in labor time, but over the course of the decades, learning curves have been applied to not only time in terms of labor hours or whatever, they've been applied to other resources, in this case cost, dollars and materials or whatever. So we're now going to assume that the learning curve approach can apply to other things. It could apply to cost as well as time. So let's assume the first unit costs $25 to make, and we expect our cost to follow an 85% learning rate. So we're going to go back to the Excel spreadsheet. If we want to know what the cost would be for the 10th unit, then we would look under the 85% learning curve column, and we say the cost of the 10th unit would be 58.3% of the cost of the first. And in fact, when we go back to the PowerPoint presentation, 0.583, 58.3% times the cost of the first, gives us an estimated cost for the 10th unit of 14.58. But what about the cost of the first 20 units cumulatively? Well, again, we go back to the Excel spreadsheet here, and now we go down to the 20th unit. We're still in the 85 percentile column, so the cumulative cost of the first 20 units is going to be 12.402, or 1,240.2% times the cost of the first. And in fact, that's what we show here. 12.402 times the cost for the first gives us an approximate cost of 310.05. Now notice, if we did not consider the impact of learning here, we would grossly overestimate what these costs would be. And that's why the learning curve viewpoint is important. Make sure again that you can get the numbers the way I did here, and that you're comfortable with using the table. You might experiment to see what your cost estimates would have been if you had a 90% learning. If you have 90% learning, these costs should be higher. If you had 70% learning, these costs should look lower. So try that out by yourself just to make sure you're comfortable with it. So here's some key points about the learning curves. Generally speaking, they describe quick improvements early on, followed by more and more gradual improvements. The lower the percentage, the steeper the learning curve. While learning curves were initially developed for direct labor, they have been applied to other types of resources, so we have to be very cautious when doing this. Give you an example. Suppose we have a product where 50% of the cost of the item consists of gold. Well, do we expect the cost of the item to follow a learning curve, or do we expect the cost of the item to follow the price of gold? Needless to say, it's probably going to follow the price of gold more than it's going to follow a learning curve approach. So we've got to be very careful when using learning curves to describe some effect other than direct labor. Practically speaking, there is a floor. Realistically, let's go back to the situation where I worked in the ice cream parlor and I made banana splits. No matter how good I got, it was going to take a minimum amount of time to make a banana split. In addition, we ought to recognize too, in the real world, you'll never see a person or a machine follow this curve perfectly. There'll be bump ups in time, there'll be bumps down, there'll be some randomness around the learning curve effect. In addition, if we start introducing new systems, how many of you have been in this situation? You get very good at using a particular software application, and all of a sudden they change it on you, and you become very unproductive for a short period of time until you learn the nuances of the new system. So the learning curve, my point is, a learning curve can be interrupted, but hopefully we will stabilize at a higher level of productivity or lower resources per unit afterwards. Finally, estimates of effective capacity must consider learning effects. And to make that point, I'm going to go through an example of how learning curves can be used in long-term sourcing arrangements. So I'm talking about a situation here where maybe a company is trying to negotiate with a supplier to provide multiple outputs over time. If you're Ford Motor Company and you're going to go with a supplier to provide, for instance, airbags for the next 5 years, you probably want to build some kind of a learning effect into the negotiated cost. So let's look at an example like this. Suppose Johnson Controls has won a contract to produce 2 engineered-to-order uninterruptible power supplies for a major power utility. So these are items with a fairly high degree of customization. We might call them engineered-to-order, make-to-order. The first unit that they produced for this power utility took 5,000 hours of labor and $250,000 of material. The second unit, which is very similar, took 3,500 hours to produce and $200,000 of materials. Furthermore, let's assume that the burden labor costs are about $30 an hour. So the question we might have is, if the customer is asking us to prepare a bid for an additional 10 units, what are Johnson's expected costs going to be? And what if there's a significant delay before the contract starts? So let's go back to the slide before. Looking at this, we actually have 2 things going on here. We have 2 pools of resources we've got to worry about: the labor hours and the material. And it seems that there's different learning going on for the labor hours and the material cost. So in figuring out what the costs are going to be for an additional 10 units, we've got to look at 2 different resources here, and we've got to consider the fact we're talking about additional 10 units, so units numbers 3 through 12. So with that background, let's solve this problem. Okay, so if we think about the hours, how do we figure out what the learning rate was for the hours? Well, the first unit, I think we were told, took 5,000 hours for that UPS, uninterruptible power supply. The second unit took 3,500 hours, so that indicates a 70% learning curve effect. On the other hand, for the materials, the first unit cost $250,000 in materials. The second unit cost $200,000 in materials. So we have a different learning effect going here, or about an 80% learning effect. All right, so with that background, then we need to figure out what the labor cost would be. So how do we do that? Well, let's go back to our table for just a second. So we have a 70% learning effect going on here. And we're talking about labor cost for the next 10 units, which will take us from units 3 through 12. So the cumulative time, labor time for the first 12 units should be 5.501 times the time of the first. But we got to remember that we've already done the first 2 units. So really what we need to do is we need to take the cumulative time for the first 12 minus the cumulative time for the first 2 units we've already done, the 1.7, and multiply that by the time for the first. So in other words, the factor expressing the cumulative time for the first 12 units is 5.501. That's if we have a 70% learning curve. The cumulative factor for the first 2, which we have to subtract out since we've already done them, is 1.7. And we multiply that by what? Correct. 5,000, which was the hours for the first UPS we made. And that comes out to be approximately 19,005 hours to make an additional 10 units. Well, if we take that 19,005 hours and we multiply that by $30 per hour, that comes out to be, assuming I can still do math, 570,150. Okay, that's just a labor cost. What about the material cost? Well, again, material costs, we're going to follow something a little bit similar, except we have a different learning rate. So we need to look at the factors under an 80% learning curve. So if we look at unit number 12, the cumulative cost, material cost for the first 12 units will be 7.227 times the cost of the first. We have to subtract out the cumulative cost for the first 2 of 1.8. So 7.227 minus 1.8. Again, the reason these are different is because we have a different learning rate going on. We multiply that by the actual cost of the first unit. So the cost of the first unit minus the factor describing the cumulative cost for the first 12 minus the cumulative cost for the first 2. This gives us a cumulative material cost for units 3 through 12, and that comes out to be $1,356,750. That's our rough estimate. We add these 2 costs together, and what we're talking about is expected cost of materials and labor of somewhere around $1.9 million. Now, this is expected cost. That's not necessarily what we're going to charge for these UPSs. We'll charge what the market will bear, right? Do not confuse price with cost, and that's something I'm sure your market professors will tell you. But the point is, if we had not considered these learning effects both on labor costs and material costs, then we might grossly overestimate what our costs would be. We might price above that and lose the business because the company who we're trying to sell this to thinks it's simply too expensive. So to summarize, we defined capacity. We talked about capacity reflecting the ability to do work over a certain amount of time. It could be days, weeks, months. We also differentiated between measures of capacity that looked at inputs to the process versus outputs. We differentiated between strategic and tactical capacity decisions. Strategic capacity decisions typically take a year or more to implement. Tactical capacity decisions are often done within the constraints set by strategic capacity. We then talked about different capacity strategies. Do we want to lead? Do we want to lag? Do we want to try to match demand? There's pros and cons of the different ones, and again, when we get to the Genentech case, you can start thinking about that. Do we want to lead capacity or not? If you're Southwest Airlines, do you want to lead or do you want to lag? Finally, we talked about some different approaches for evaluating capacity alternatives. The classics, economies of scale and different points and break-even points have been covered in a lot of different courses, but it's good to review them. Expected value analysis, where does it come into play? Well, it comes into play when we're trying to take multiple options in terms of capacity, multiple possible demand scenarios, and put out that information in a way that's meaningful. Finally, I talked about learning curves. And the idea behind learning curves is that resources become more productive over time, and as a result, the effective capacity for a pool of resources will increase due to learning. And we have to consider that both in planning our own internal operations and in negotiating with suppliers or negotiating with potential customers. Now, I'm going to have some additional information out there on the website that will look at learning curves in more detail with some more realistic types of examples, and also maybe some other additional expected value analysis based on some examples in the book. So take a look at those.